Welcome back. Today I will say some properties of compact set, and this property actually very important for her study. So at first I will highly recommend you please pay attention in today's video. We all of us know, consider XD a metric space. It is compact, the metric space is compact if every open cover has a finite subcover. Okay? Then this metric space is said to be compact set. As for example, consider the metric space Z. And this is the set 1, 2, 3, 4, minus 1, minus 2, minus 3, so on. Z is not compact because if we consider one open cover minus n comma n, obviously this is the cover of Z, this is true, but there does not exist no finite subcover. Okay? Also, we can consider one open cover such type V half, the point, consider the point as P, where P belongs to all integer, that means such type of ball contain the point with half radius. Obviously this is the open cover of this set Z, but there exists no finite subcover. So obviously Z is not compact. In the previous video I have discussed this topic elaborately, and first property of compact set is finite intersection property. And the property is, if consider tau, consider here tau, the set considered as a tau, be a collection of the set, and we say tau has a finite intersection property if the intersection of any finite number of set is non-empty. That means intersection of any finite number of set, if non-empty, then this collection is called as a finite intersection property. Okay? Now I will see one relation based on finite intersection property. And the use of this finite intersection property in compactness is when the set X is compact and given any finite collection of closed set of the set X, then by finite intersection property we can tell intersection of this collection always would be non-empty, means not equal to 5, and this is true when the set X is compact. And this proof today I will not prove, because this proof is actually very vast proof, but the concept is very easy. In any standard book has given this proof. At first see the proof, and if you have any queries about this proof, then do comments in comments box. Today I will see one example based on this proof. This example is very interesting and very conceptual. First know, any closed and bounded set in R always compact. So this type of set always compact. Also, if we consider this type of box 1, 2 cross 3, 4, this is also be compact set. And today I will discuss in RK A1 B1 cross A2 B2 up to AK BK, this type of box is compact in RK. Okay? Today's goal of this lecture is this part. Okay. So we all of us know in R2 or complex number all closed ball be compact. Now I will see our next goal of this lecture. Actual goal of this lecture is I will see in RK this type of box always be compact. I will prove this example by contradiction. At first, consider this type of box is not compact. Suppose consider this type of set as a F. Suppose U is cover of the set F. And since I have considered this set is not compact, so obviously it does not have finite subcover. Here the set has considered it in RK, but for calculation, easy calculation, consider R2. Then the box would be such type A1, B1, A2, B2. Okay. Lastly, I have considered this set as a F, and notice here I have considered it R2. Now it divides into 4 sub boxes. Here since I have considered R2, so it divides as a 4 sub boxes. R3 it divides 8 sub boxes. Similarly in R4 it can be divided 16 sub boxes. So obviously in RK this F can be divided into 2 to the power k sub boxes. Okay, have you understood? Well, and I have considered it U is cover of the F. That means this type of U is such type who is covered the set F. If each sub boxes contain finite number of subcover, then our given cover U does not have a finite subcover. This consideration would be wrong. So consider one sub boxes contain infinitely subcover. Consider these sub boxes and consider these sub boxes as F1. Consider the sub boxes F1 contain infinitely many subcover. Okay. Now let's look the diameter of the set F. Here the diameter of F is delta. So obviously the diameter of F1 would be delta over 2 because I have divided these boxes as a 4 part. So since F1 contain obviously the set F and diameter of F1 would be delta over 2. Now I will study about the sub boxes F1. Now just divide the sub boxes as a 4 part and consider one sub boxes not contain finite subcover, and consider one part of this F1 does not contain finite subcover, and consider this is as a F2, and then obviously F1 contain F2, F2 contain here F2 contain F1 and F1 contain F, and since diameter of F1 is delta over 2, so obviously diameter of F2 would be delta over 4. Similarly, we can divide F1 as a 2 to the power k sub boxes, and one of them say F2 does not contain finite subcover. Okay. So notice here F2 contain F1 contain F. So same way I will get one decreasing subsequence, and this distance diameter would be delta of Fn would be delta over 2 to the power k. This distance would be smaller and smaller and smaller because this is the decreasing sequence. Continuing this process, I will get one decreasing sequence of such type, and the diameter of Fn would be, since here Fn, so diameter of Fn would be obviously delta over 2 to the power n. Therefore, I have got some compact set which is decreasing. That means here we can apply the finite intersection property in compactness. I hope my all viewers have understood this graph easily. How I have approached this concept, I hope my all viewers have understood. Here, what is the finite intersection property? How here applicable the finite intersection property? Here, each Fn is closed, non-empty and bounded. Hence, by finite intersection property, since here the sequence be decreasing sequence, so by finite intersection property we can tell intersection capital N equal to 1 to infinity Fn not equal to phi. That means obviously there exists at least one point in the intersection of Fn. This is the finite intersection property. At first see the picture. Here I have considered F1 which does not contain finite subcover. Then I have also divided F1 in sub-interval, and I have considered F2 has a no finite subcover. Then again divide F2 in 4 part, and consider this is F3 which has no finite subcover, and this is continue, and consider X which lies between this Fn. Since X is the intersection of this Fn, I have considered it. So consider X be the intersection of this Fn, and since the set F is covered by the U, I have considered it. So obviously X contain these patches, but since U is a open cover, so obviously there exists some open ball B of XR, where R be the radius of this ball which contain this open cover. Okay, that means since U is open, that means there exists R greater than 0 such that B of XR contain in U. Then choose one capital N which is large enough such that delta over 2 to the power n obviously would be less than R. So there exists a ball with radius delta over 2n which obviously contain B of x comma delta over 2 to the power n, obviously contain the ball B of x comma r. Okay, here I have seen there exists subinterval Fn whose length is delta over 2 to the power n. If this subinterval be Fn whose diameter be delta over 2 to the power n, that means if here consider x, that means the ball with center x and radius delta over 2 to the power n, obviously this ball will contain Fn. That means Fn is contained in the ball b of x comma delta over 2 to the power n, and b of x comma delta over 2 to the power n contain the ball b of x comma r. So obviously this is also contain b of x comma r. So this is the cover, since the u cover the set fn, so this is contained in the open cover u. That means, notice here very interesting thing. Here I have got one cover who is contain the divide part fn only, but I have considered fn does not contain any finite subcover. But here I have got one open cover who is contain the set only fn. That means obviously this cover obviously be finite subcover. That means our assumption is a wrong assumption. Have you understood? I have considered f1, f2. This sub-interval does not contain finite subcover. But I have got one cover of u who is only covered the set fn. That means obviously this cover be finite subcover. So our assumption is a wrong assumption. I have assumed u is a cover of f such that it does not have finite subcover. That means our assumption is a wrong assumption. That means u is a cover of f that contain finite subcover. So obviously the set f is a compact. I hope my all viewers have understood how to prove compactness, how here use the property of finite intersection property. I hope my all viewers have understood clearly. Okay? Well, the concept is actually very useful for higher study. So I have proved this concept elaborately. Now I will say one question of sequence of function about compact set which had come in n.b.h.m 2014 exam. The question is, consider gnx equal to n times f of x plus 1 over n minus fx, where the function f defined from real number to real number and which is continuous function. Then which of the following statement are true? Option 1. If fx equal to x cube, then gn converges to f prime uniformly on the set R as n tends to infinity. Option 2. If fx equal to x square, then gn converges to f prime uniformly on the set R as n tends to infinity. Option 3. If f is differentiable and if f prime is uniformly continuous on the set R, then gn converges to f prime uniformly on the set R as n tends to infinity. The question is, here gnx equal to n times f of x plus 1 over n minus f of x. Okay? In the first option, fx equal to x cube. Then, since gnx equal to n times f of x plus 1 over n, that means this would be x plus 1 over n cube minus x cube. Okay? Which is equal to x plus 1 over n cube minus x cube divided by 1 over n, and after calculating this value would be 1 over n square plus 3x over n plus 3x square. Then obviously limit n tends to infinity, gnx would be 3x square. Okay? That means Gnx converges pointwise to the function 3x square. Now we have to find, is this convergence is uniform convergence? For this, I will apply m.n test. Supremum here, since the domain is whole real number, that means supremum x, absolute value of fnx minus fx, and which is equal to actually supremum 1 over n square plus 3x over n. Okay? Here x belongs to real number. Obviously, since here depends on x, so obviously this supremum value does not tends to 0. Have you understood? Our next option, here fx equal to x square. Then similar to before, since here fx equal to x square, then that means Gnx would be x plus 1 over n whole square minus x square over 1 over n. Obviously Gn converges to 2x. So we have to check, is this convergence is uniform? So supremum x belongs to R, Gnx minus Gx, then this value would be supremum x belongs to R, Gnx would be Gnx minus Gx, that means this value obviously would be 1 over n square, and as limit n tends to infinity, obviously this value tends to 0. So fx equal to x square, then obviously Gn converges to prime uniformly on the set R, because fx equal to x square, here Gn obviously converges to a prime. And notice the third option. Third option indicate if f is differentiable and f prime is uniformly continuous on the set R, then Gn converges to f prime uniformly. Here, since Gnx equal to n times f of x plus 1 over n minus f of x. Okay, this is equal to actually f of x plus 1 over n minus f of x over 1 over n, and limit n tends to infinity, Gnx equal to limit n tends to infinity f of x plus 1 over n minus f of x over 1 over n, and obviously this value is equal to a prime x. That means Gn converges to pointwise a prime x, but given the a prime is uniformly continuous on R, so obviously this convergence would be uniformly convergence, okay, on the set R. Have you understood? That means option 3 also right option. Have you understood this option? I hope my all viewers have understood clearly. Today I will stop here. In my next video, I will discuss some another properties of compact set. Okay? See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.